so I promise not to take too much of your time. So the title of my talk is Dynamics of Floquet Systems with Duality Defects. And this is work that over the years has been done with many people. It all started with my colleague at NYU, Yifan Wang, and former postdoc, Mao Tian Tan, who is now in Korea. And the results I'll present today, primarily all the heavy work was done by Fei Yan, who's a postdoc at Brookhaven National Lab, and the results appear here. So this talk is about dynamics of closed quantum systems, and in particular Floquet dynamics, but I will also talk about unitary dynamics with a time-independent Hamiltonian. And the idea is basically that the last few years knows a lot about topological properties under out of equilibrium conditions, but what has been kind of overlooked are things known as topological defects. So they are kind of, people often describe these topological defects as some kind of topological symmetries, often going under the name of non-invertible symmetries. So what I'm interested in studying, and I hope I can convey this during my talk, is how these duality defects or topological symmetries can be introduced in an out of equilibrium setting, and what are their consequences? How do we see it in the dynamics? So that's going to be the goal. And moreover, since symmetries often constrain dynamics, what I would like to show is that when you take into account these new kinds of symmetries, you can actually get some constraints that prevents the system from heating as much as it would have done if these symmetries were absent. So that's two goals of this problem. So again, here is a kind of a very high-level introduction, which I think most of you don't really need to hear it, but I'll just go over it anyway. So why study Floquet in the first place? So there are practical reasons. So for example, in Floquet, what you're doing is you have some initial wave function, and you are time evolving it with respect to a time periodic Hamiltonian, or you are just, or maybe you don't even have a Hamiltonian, but you have some unitary, and you are just stroboscopically evolving the system forward. So this is a natural setting, for example, in experiments in Google's devices, where you start with some initial configuration of qubits, and literally what you are doing is applying single-site and two-site unitaries. At the same time, if you take a solid and you shine a laser on it, then you also have access to these kind of time periodic Hamiltonians. The second practical reason for studying Floquet dynamics is that even if you were given a static Hamiltonian, you do something known as a Trotter decomposition, and whenever you have a finite Trotter time, you really have Floquet dynamics. A third practical reason is that for many integrability people, you will appreciate this, that transformative method is a very general way to study many integrable models. And when you take these transform matrices and you analytically continue from imaginary time to real time, you get Floquet dynamics naturally. But besides these very, very practical reasons for studying Floquet, what we've also learned in the last decade or so is that when you Floquet drive a system, you get new out of equilibrium phases that are completely absent in static systems. And by now, people understand this very well, and there are nice review articles which really point you to topological phases of matter that are new when you Floquet drive the system. And so it's natural to start with these kind of topological phases of matter and then look at the effect of these duality defects. Those aspects have not really been studied that well. Okay, so my goal is going to be that I will first give you some introduction to band topology. So this is a kind of a less exotic version of topology. This is not like toric chord type topology where you have topological order. I'll first tell you about band topological insulators for static Hamiltonians. Then I will tell you about how they get modified when you do Floquet driving. And then I'll introduce duality defects. So what are band topological insulators? So as the name, they often go also under the name of symmetry predicted topological phases or free fermions. And as the name suggests, they're really quite boring objects in the sense that the bulk of the system just looks like a band insulator. There's a valence band and there's a conduction band. But at the boundary, you have edge modes. And what's interesting about these edge modes is that you cannot remove them if you preserve certain symmetries in the problem. And moreover, the symmetries you're talking about are not crystallographic symmetries, because if they were crystallographic symmetries, then you can just put disorder and get rid of them. The symmetries we're talking about in the system are really difficult to remove. So for example, you're talking about time reversal symmetry, or you're talking about particle hole symmetry, where particle hole symmetry arises when you have some superconducting systems and the valence and conduction bands are those of non-interacting Bogoliubov quasiparticles. And then when you have both time reversal and particle hole, you can construct a unitary operator known as a chiral operator, and then so depending upon whether the system has time reversal or not, particle hole or not, or whether the system is even or odd under these anti-unitary symmetries, and whether you have chiral symmetry or not, then you have a periodic table such as this one. It's quite remarkable. So basically what you do is you take a Hamiltonian, you find out what discrete symmetries it has, and then you look at what dimension you are in, and if there's a non-zero entry, that means you are allowed to have one of these non-trivial topological insulators in the sense that the boundary has a conduction band and a valence band, but the boundary has these edge modes which cannot be removed unless if you're preserving one of these symmetries. And so I have pointed out some very famous examples in circles, like this is the integer quantum Hall effect, this is the polyacetylene, also known as the Schiefer-Heger model, and this is the Kitaev chain. So in my talk, I'll really be talking about Kitaev chain and Floquet driving it and putting in interactions, and it's in this context that we will see these duality defects show up, and so that is the example that I'll be studying in detail. Okay, now let's Floquet drive the system. Why does Floquet driving give you new topological phases? Well, the simplest way to understand it is that when you have a Floquet system, you have a unitary. And there is a very general way to write this unitary. You write it as a product of two terms. One is the standard one, where you have time evolution with respect to a time-independent Hamiltonian. But then it comes with this product of another unitary operator phi, which is completely time periodic. So when you do a classification of topological insulators, not only do you have to classify the static part, all the different HF that you can have, but you also have to classify these unitary operators, which are perfectly time periodic. And because of this additional ingredient, you have a little bit more structure. And it turns out that the structure is really quite simple, in the sense that if I have a static system which has a topological invariant, say Z, then under Floquet driving, it turns out that it gets enriched to Z cross Z. So the periodic table that you get here is pretty much the one that I showed in the previous transparency, except that wherever there's Z is Z cross Z, wherever Z2 is Z2 cross Z2, etc. And for people who like more mathematical way of looking at things, there's this cohomology group type construction you can do for bosonic SPTs, where if the static system had a group G, then the Floquet system corresponds to a group Z cross G, where Z is just because you have discrete time translational symmetry. And this additional thing ends up giving you a little bit more structure to the topological phases of matter. So then again, as I mentioned before, I'm going to be focusing on this particular family, and this one is the simplest model where you see the duality type defects show up. So again, the motivation is that, as I said in the previous transparencies, all this knowledge about topological systems really relies on identifying what are the relevant symmetries in the problem. But then there's been recently a lot of interest about trying to expand our view of symmetries. Why should we only consider symmetries that you encounter in undergraduate class in quantum mechanics, which are just unitary or anti-unitary symmetries? There are more fancy symmetries. They go under the name of generalized symmetries. And for me, the more interesting, I'll focus on a kind of generalized symmetry, which are these non-invertible symmetries. The way you think of them are that it is not a pure unitary symmetry, but a unitary symmetry times some projector. As a result, it's non-invertible. And so how do this kind of non-invertible symmetry manifest in the dynamics? So it shows up, these kind of non-invertible symmetries shows up very quite naturally in the Kitaev chain, which in the spin chain language is just the Ising model. And so again, this is a little bit of a review. So just to remind you, the Kitaev chain is one where you have spinless fermions hopping between nearest neighbor sites. There is a local chemical potential, and then there is this p-wave pairing. If you do a Jordan-Wigner transformation, and if this hopping T and the superconducting order parameter delta are equal to each other, you just get this transverse field Ising model. So sigma xx and mu. And then with open boundary conditions, you have edge modes in this problem. These are just unpaired Majorana edge modes. And what's cool about it is that these Majorana edge modes are not just tied to the ground state of the system. It's that you see them in any eigenstate of the system, even at infinite temperature. That is because these operators are what are known as strong zero modes, in the sense that these are operators that commute with the Hamiltonian, and they anti-commute with a discrete symmetry in the problem. As a result, their existence implies that the entire spectrum of the system is doubly degenerate. So there is an even parity sector, and there's a degenerate odd parity sector where the even state and the odd state are related to to each other by the application of this edge mode. And so what I think, what makes these systems really special is, while in the case of the bad topological insulators, it is well known that by the time you raise the temperature to be of the order of the gap, you don't see any edge modes. In this particular case, the temperature can be infinite, and yet you'll see these edge modes because of this property, that these are really operators that commute with the Hamiltonian. In the language of spins, for those of you who are more comfortable with the spin language, if I write the Hamiltonian in terms of spins, so that you have the transverse field Ising model, this edge operator has the following structure. It is, when mu is 0, is just sigma x on the first side, and when mu is not 0, it is still a localized operator at the boundary of the chain. It's localized as long as mu is less than j, and formally the way to write it is that it is sigma x1 plus mu over j to the times the sigma x1, sigma z2, and so on and so forth. So it's a chain with longer and longer terms, but the prefactor also becomes smaller and smaller before, as the chain becomes longer and longer, so it's a very localized operator. It becomes completely delocalized when mu is equal to j, which is also the point at which we have the topological phase transition from the trivial phase to the non-trivial phase. Okay, so now again, since later in my talk I'll be showing many of these kind of plots, I just want to show you that suppose I didn't have an analytic solution for this edge mode, then how do I know that such an edge mode exists? It is by studying something known as an infinite temperature autocorrelation function. So as I showed you in the previous slide, when mu is 0 or small, the edge mode is literally sigma x on the first side. So what you can do is just study the infinite temperature autocorrelation function, sigma x at site 1, at time t, sigma x at type 1, at time 0. This is infinite temperature because note that you're doing a trace over the full Hilbert space. And the signature of a long-lived edge mode is that this autocorrelation is going to be extremely long-lived. If I had chosen any other seed operator, as is done here, with corresponding to the green and the red lines, you would find that the autocorrelation decays in a time of order j, and then it just oscillates around because it's a free system, so there are recurrences and stuff like that. But literally, if I didn't have any analytic solution, what I would do is I'll play around with different seed operators, look at the infinite temperature autocorrelation, and this long-lived autocorrelation is a signature that there is such a edge mode.
Sorry, just to confirm, this
yes.
blue plot is for sigma x and green and
yes,
sigma
yes.
y and z.
Correct.
Okay.
Yes. Now let me go forward. Now let's do Floquet driving. And as I promised you, with Floquet driving, everything will become richer. And as I said to you that when the static system had z, the Floquet becomes z cross z, and I will show you how the z cross z manifests. So now take the Kitaev chain and then just Floquet drive it. So here, the details of how the Floquet driving is happening is not important. In this particular case, we literally took a chemical potential and made it time periodic. And then what we did is that because although the energy is not conserved, you still have some notion of a quasi-energy, which is a phase of the Floquet unitary after one drive period. So what we're doing here is plotting the quasi-energy in the system. And this quasi-energy better be restricted in the first Floquet-Brillouin zone, which is between minus omega over 2 to plus omega over 2, where omega is the drive frequency. And when the frequency is kind of high, so that you're more or less in the Hamiltonian limit, you have the zero mode. So this is being done with open boundary conditions. So this is the familiar topological phase of the static system, and you're just seeing it manifest in the Floquet problem. But then when you change the drive parameters, you have a topological phase transition where you have new edge modes appear. So this Z cross Z is what I was saying, that you have this new edge mode that is now appearing at precisely omega over 2, and it cannot be removed as long as you are preserving time reversal and particle hole symmetry. And yes, and the way it manifests is that if I look at the edge mode autocorrelation function, you'll find it to be not only long-lived, but that it is flipping between 1 and -1 for even and odd times. Okay. Right. Now, the other thing I wanted to show here is that let us just take this Floquet unitary. Here is a very nice phase diagram which shows where you will get these, where you will get the edge modes corresponding to the static system, and where you will get new kinds of edge modes corresponding to Floquet driving. So on the x-axis you have the prefactor of the transverse field term. On the y-axis you have the prefactor of the Ising term, and what you and this part of the phase diagram, you can think of it as the high frequency limit. So you have the topologically trivial phase if the transverse field is too large, and you have the topologically non-trivial phase if the Ising field is very large. So this is the boundary separating the trivial phase and one where you have a zero edge mode. But then when you start making the period smaller, you have new phases appearing. So this is the one where you have not only a zero mode, but also this pi mode at the Floquet-Brillouin zone. And then there is this other phase where you have purely a pi mode, and there are phase transitions separating these 4 different phases. So this is again repeating the fact that you have not just Z, but Z cross Z. Okay. And so even in the Floquet case, you find that you can construct the edge mode operators, the conserved edge mode operator. But the new thing is that while the zero mode gives rise to a perfect degeneracy between even and odd parity sectors of the Floquet unitary, the pi mode now also leads to an a pairing of the quasi-energy spectrum, but the even and odd spectra are actually separated by pi over t. So that's the new thing. And then as in the example, okay, so this is not, yeah, and as in the example I showed you before, numerically also, if I choose the appropriate seed operator by seeing how rapidly the autocorrelation functions decay or persist, you'll know whether you have such an object or not, even if you cannot analytically solve for it. Okay, so now let me go back to my motivation about this non-invertible symmetries and how do they show up here. So the Ising model or the Kitaev chain has this non-invertible symmetry, which is the Kramers-Wannier duality. What it literally means is that you have the standard symmetry, which is the Z2 symmetry, which in the language of fermions is fermion parity. But you also have another one, which is the Kramers-Wannier symmetry, which says that if you take sigma cross sigma, you get 1 plus psi. So this is why it's non-invertible, because on the right, if you think of these as unitary operators, then you would do sigma cross sigma dagger and get only 1, but instead you get 1 plus psi. And it's because of this projection, the name non-invertibleness is associated with it. But you actually already see it in all the things that I've told you so far, you already have it. In what sense? So this sigma can be thought of as the Majorana mode on one end of the chain and the Majorana mode on the other end of the chain. And this fusion just corresponds to taking those two Majoranas and bringing them together. When you bring two Majoranas together, you get a complex fermion, and the complex fermion can either be occupied or empty. And so that's what the right-hand side means. There are two possible eigenvalues for the right-hand side. One eigenvalue is just the fermion being occupied, and the other corresponds to the fermion being empty. So in everything I've told you, you already have the non-invertible symmetry. But I want to see its effect in a more direct way. And so I want to kind of do other things with it. So I want to, for example, introduce a twist corresponding to this Kramers-Wannier duality transformation. And that would require me to modify my Hamiltonian or unitary in some particular way. And it's kind of difficult to guess how to do it. And so the formalism that, at least for me, is the clearest, is to literally start building lattice models starting from a certain fusion category, and then introduce defects in that formalism. And then you can see literally what kind of lattice models have these duality defects. And you can do it both for integrable models as well as non-integrable models. And then you can ask the same question, are there localized edge modes in the presence of these duality defects? If the model is not integrable, do these edge modes decay immediately, or do they take a long time to decay, or are they exactly conserved? So that's the kind of story I'll be focusing on now. Okay, so again, yes.
So I guess the hope of, I mean, obviously the free fermion model has many crazy symmetries, but the hope of focusing on this one is that it might be generic in interacting systems as well.
Yes, that's right. That's the reason why I want to do it. So I literally want to work with a model which only really has these two symmetries, one sigma and psi.
Yeah, okay.
And then I want to see what the physical consequence of that is. And then I also don't want to just tie myself to free fermion systems. I want to have interacting systems. And I want to see, again, what is the signature of this kind of sigma in these interacting systems. And for me, the easiest way to arrive at general interacting models which have these, which have this Kramers-Wanier duality is to use this language. So this is a language which has been used quite a bit in these previous papers. That is the language of anionic chains. And there the basis is what is known as the fusion basis. It's as follows. So I think for many of you, you already know all this, but maybe for younger people in the audience, I should just explain this. Suppose I wanted to construct a 1D problem using this fusion basis. What does it mean? So imagine you just have a lattice sites which correspond, actually you have lattice edges, and you put, if I'm working with Ising anions, then I put 1 sigma, or there are only 3 objects in this Ising fusion category: unity, sigma, and what I was calling psi is now, become epsilon. So epsilon is my Z2 symmetry. So put these objects on these edges, but take care that they obey the fusion rules. So you cannot just put anything. And moreover, you might have also heard that the problem with these fusion bases is that you often do not end up, with anionic chains, is that you often do not get models which are simple tensor products. But indeed you can if you do the following. You take these external legs and you fix them. So let's take these external legs and fix them to be sigma. So then you can have the following values on the edges. Sigma cross sigma can be either 1 or epsilon. So that's why you are forced to have every alternate side being taking values 1 or epsilon, and the other ones being sigma. Okay, so so the sigma sites are like the dual sites, and the ones with which 1 and epsilon are literally the Ising model, because the sites can take only 2 possible values, 1 and epsilon. So this is my basis. And now I want to understand what do operators do to this basis. Then the only non-trivial operator is really the insertion of the epsilon operator. There's nothing else that you can add. I can't put a sigma because then the outgoing legs will no longer be sigma. So if I want the outgoing legs to be sigma, I have to put this epsilon operator. And then you will find that if the epsilon operator is put on the sigma link, the matrix element of this object is precisely ZZ. And if I want to put if I put the epsilon operator on the link which has 1 or epsilon, then the matrix element of this object is exactly X. So what you have found is that, quite simply, without this is just giving you the same terms as the Ising model. And then you would say, oh, well, isn't that a really complicated way of getting the Ising model? Well, I mean, the advantage of doing this is that now you can start putting defect terms. And I do not know any other way to get defect terms without using this language. Maybe experts would use something else. So if I want to now put a defect term, it literally corresponds to inserting a sigma on this line. So what it does is that, you see, if on the left-hand side you had sigma h, this defect term forces you to kind of flip it. So you go from h sigma. So it's known as a duality defect. And then when you, a duality twist. And then if you look at the matrix element of the object, if I put the epsilon operator here, without the defect, this would have been just ZZ, but with the defect, you're forced to have ZX. Okay? So introducing the duality defect in the model tells you that the place we have put the duality defect, instead of ZZ, you should have ZX. Now, what's very nice about this formalism is, as promised, you can also get non-integrable models. So how do you get non-integrable models? You put epsilon on neighboring, you put them together on neighboring sites. So if there are 2 epsilon operators acting on the sigma sites, it turns out this matrix element is just ZZ. And if these 2 epsilon projectors are acting on the HH sites, where H is 1 and epsilon, it turns out that this corresponds to the matrix element XX. So you are getting a non-integral model, and if the prefactors is the same, you can see that these are Kramers-Vonnier symmetric. Because Kramers-Vonnier takes ZZ to X and X to ZZ, and so these are symmetric under a Kramers-Vonnier transformation. Okay, but this is also something you wouldn't have needed to do all this fancy stuff. But what is really helpful is that if you put a duality defect, then you know exactly how to modify the terms in my interacting model. So in the presence of the duality defect, you get Zx, next nearest neighbor terms, and then you get Zxx, and you also get Xzz. Okay? And I was told that these are also go by the name of TT bar deformations if you go into the continuum. Okay, so now let me just, and then another thing is that there is yet another way to get all these terms, but I do not know how to generalize it to models to systems where you have non-invertible symmetries that are not Kramers-Vonnier types, but other kinds. So one way to generate these other terms is that you literally do a Kramers-Vonnier transformation, but on half the chain. So when you do Kramers-Vonnier, what you do is the following. Suppose I have sigma, the dual sides are the even sides, and let's say the Ising spins are on the, the dual sides are the odd sides, and the Ising spins are on the even sides. Then the duality transformation, what it does is that it literally takes the spin on the even sides, such that if the odd sides were up or down, you make the spin on the even sides be along poly x equal to 1. And if the spins were up, down, or down, up, then you should take the spins in the even sides to be along sigma x equal to minus. This is what you would do in the bulk. But if I was doing a half-chain Kramers-Vonnier, then it's kind of tricky. What you do is that where the chain ends, the boundary of the transformation, you, instead of having the sum of the poly z's on neighboring sides, you just put one of the polys. And then it turns out magically that if you do this, you'll recover all the terms that I wrote down previously. So okay, to summarize, what we get when you put a duality twist is the following. You get ZZ, you get X. Then you get, if I want to break integrability, you get next nearest neighbor ZZ, you get nearest neighbor XX. And then you get all these defect terms. So introducing a duality twist means that at the point of the twist, you remove the transverse field. And where there was a ZZ term, you change it to a ZX term. But then you also have these other terms which are really not exactly solvable. The ZX, I mean, if you write it in terms of free-form here, these are interacting terms. So these are non-integrable models. So what is the physical consequence of this? So it turned out that what we were doing here is also tied to something known as weak integrability breaking deformations. So we learned about this. These are some papers written by Sorachi and Mitra. So what did they show? They showed that if you started with an integrable model, so that means you have a bunch of charges where these charges commute with each other, you can actually do a transformation to the model such as this. dq d lambda is equal to I x lambda q lambda. If literally the transformation are as follows, you can show that all the charges still commute, are conserved. So this is a way to make sure that you are still generating a bunch of integrable models. The catch is that quite generally the new charges that you get, even though they all commute with each other, they're highly non-local. In other words, these densities are not just, have a finite weight around side j, but are like, decaying, are extremely long range. So on top of that, if I want to have charges that are quasi-long range, it puts strong constraints on x. So they explain that there are only some special x's. If you choose them, then not only are these charges conserved, they also constitute to be quasi-local. So they explain this very nicely in their paper, but still they are not, there's only still quasi-local in the sense that this charge density, while it's peaked at j, it is still exponentially decaying away from j. It doesn't have a finite weight, which is exactly 0 after some sites. So if I want to create a truly local model, then one way to do it is to think of this expansion x as a power series expansion in lambda, and then you just truncate brutally at lambda. So of course, if you do this truncation, these charges are not exactly conserved, but what's nice is that if I truncate the Taylor series expansion at lambda to the L, it turns out that these charges commute with each other to order lambda to the L, which means that if I look at the dynamics of these charges, they'll decay very slowly. You know, you won't have, if this L is 3, the decay will be at least lambda to the 6 or something like that. So it's going to be much slower than naive, broken integrability, where typically you get Fermi-Golden rule type decays where everything would just decay as lambda square. So this is a nice way to suppress the decay rates in your problem. And then it turns out magically that if you take your X transformation to be this one, it's some very complicated one in terms of bilocal operators, and moreover, you do a Taylor series expansion and you just keep the leading term. You keep the leading term and then you get precisely this model. So this Kramer's one-year type symmetric model is also directly related to a weak integrability breaking deformation. So it's all very nice, and there are many different ways of coming to the same result. So we were very inspired by this, and then what Faye did is that she went back and showed that all these other terms that we have in the presence of a defect that I've written here can also be done as a weak integrability breaking deformation, where what you do now is that these charges that you're using to do the deformations already has the defect term in it. So you start with an integral model which has a defect term, and you do this weak integrability breaking deformation, and you generate everything here. So that already tells us that if the dynamics is there's going to be something interesting, things will decay much slower than if I was just breaking integrability in a naive way. Okay. Okay, so now I'll just give plots and results. So this should be easy. Okay. So result number 1 is that, let's go back to this model and just keep this, and this term. So everything, it turns out, when you do a Jordan-Wigner transformation, can be written in terms of free fermions. So ZZX, and then just this twist, ZX. You write it in terms of Jordan-Wigner transformation. Everything is in terms of, is quadratic in Jordan-Wigner fermions. So this is a Ising term, this is a transverse field, and this is a twist term. Now, the only thing is that at the position of the twist, you have this non-local term, omega, and this corresponds to the fermion parity in the problem. But the parity itself, or the Z2 symmetry, needs to be changed. So if the Z2 symmetry was product of all gammas, now in the presence of the twist, it's a little bit more subtle. So for example, here I've written it in terms of polyspins. If without the twist it was products of all x's, now it turns out to be product of all x's except 1, and one of the x's is now replaced by y. And this obscure change is really quite remarkable, because it turns out that if I write it in terms of fermions, this omega actually contains all the fermions except 1. So it's a strange object. It actually contains odd number of fermions. So this model with a twist actually has odd number of fermions. I've never seen a model like this before. And it seems like a very strange model, but the way I understand it is that it's a very physical model in terms of spins, right? But the moment you write it in terms of fermions, while that gives you a tool to study the problem and solve it, it's a strange model. If I told anyone that I have a model which has odd number of fermions in it, it'll just surprise people. But the fact that there are odd number of fermions is extremely important, because it turns out that this model has to have a zero mode, no matter what. So that was another surprising thing to us. So that means that there is a Majorana mode no matter what coupling you take in this model, J, G, whatever. As long as J and G are not equal to each other, you have a localized Majorana mode at any energies. So that was result number 1. This is not so important. This is the, so you can always ask, well, after all, our Hilbert space consists of even number of Majoranas. So what about the left of Majorana? So this is just showing you that this is just showing you the localized zero mode. So as I said, this is a strange model which has odd number of Majoranas, so you're forced to have a zero mode no matter what, and this is just a plot of the zero mode. The localization, as you would expect, depends on the ratio of J over G or G over J, but whether J is greater than G or G is greater than J doesn't matter. For as long as the couplings are are unequal, you get a localized mode with a localization length which is related to the ratio of J over G. If they are if J and G are equal to each other, then you still get a zero mode, but it is completely delocalized along the chain. Okay. Next thing is What about the leftover Majorana? Because after all, our Hilbert scale still consists of even number of Majoranas. So the leftover Majorana is really is this object. If I look at its dynamics, after each Floquet period, it just becomes a longer and longer chain. And if I look at its autocorrelation, it decays very fast. So it's not a long-lived mode. Now, if this was a physical model in the language of fermions, then this would have been the other zero mode, and you would have got a pair of zero modes and so on and so forth. But this one is not what you get when you're starting from the spin chain. Okay, now I want to talk about this localized zero mode and its relation to the Kramers-Warnier duality transformation. So imagine that I have just a chain where I have spins on odd sides, and so 1, 3, 5, 7, 9, and 11. And let's say that I have put this twist between sites 9 and 11. And what I have are completely homogeneous couplings. Also, another thing I want to mention is that you can make the couplings inhomogeneous and you still get the same physics, right? Because this is just counting, that I have a unitary matrix which is orthogonal and its dimension is odd. So it has to have a zero mode. So you can take whatever couplings you want, you'll get a zero mode. For these choice of couplings, the zero mode is localized, say, at site 1. Okay? It's localized around site 1. Now I can do a local unitary transformation which moves this duality twist from between sites 9 and 11 to between sites 9 and 7. Okay? So it's a combination of Hadamard and something else, control Z's. Interestingly, what happens is the zero mode that you get in the model doesn't move. So you can keep doing these local unitary transformations and moving the position of the twist, but the zero mode doesn't move. But what happens is that the zero mode, the region between the zero mode and the twist actually undergoes a Kramers-Warnier transformation. So if you look a little carefully at this plot, then you'll find that when you move the duality twist, what was the Ising term becomes the transverse field, and what was the transverse field becomes an Ising term. And then you can keep doing this, and so all you have done is you've done a series of Kramers-Warnier between where the Majorana is located and the new location of the twist. So the meaning of the Majorana then is clear. It is basically acting like an interface between a region where J is greater than G and a region where J is less than G. So it is the way you would think of this single isolated Majorana with a duality twist, except that people usually study it in the ground state of the model. Here you have a highly excited state. There's no sense in which one side of the Majorana is a ferromagnetic phase and the other side of the Majorana is a paramagnetic phase. Everything is at infinite temperature, there's no order, but yet this zero mode is long-lived, and doing this local transformation just is doing some Kramers-Warnier in the language of the couplings. So that's one thing to notice here. And now I will switch on interactions. Okay. So what happens with interactions? So let me just remind you what happens with interactions if I didn't have a duality twist, if I just had open boundary conditions. If I had open boundary conditions, then you remember you have a localized edge mode on the left end of the chain and the right end of the chain. And so even in the non-interacting case, because of tunneling, these edge modes are not long-lived, right? And the way to see it is that if I looked at the autocorrelation function, it lives for a time which is of the order of exponential in system size, but then eventually the two modes hybridize, and so the autocorrelation decays and oscillates, right? So this final decay is entirely because these edge modes are appearing and there's some tunneling. And you can do that both for the zero mode and as well as the pi mode. And then when you switch on interactions, what happens is that if the chain is long enough, then the interactions end up causing the particle to decay before tunneling between the two edge modes have set in. And so the way you see it is that these autocorrelation functions, they have a finite lifetime, but it's independent of L. So when it's basically the interactions which are driving the decay of these edge modes, you get these you get a lifetime which is primarily interaction dependent and not system size dependent. Unlike in the free case where the decay times are all system size dependent, right? So then, but again, these are known as almost strong modes, and these time scales can be very, very long. So the question that you can ask is, what happens to the zero mode if I break integrability? So this is actually what we first attempted to do before I knew all this fancy stuff about breaking integrability in a symmetric manner. This was a very crude way of breaking integrability. So you start with the model ZZ, X, and ZX, and then you just break integrability by doing next nearest neighbor ZZ, or next nearest neighbor XX. Okay. Then, but still you get a surprising result. So you look at the autocorrelation of the operator which has overlap with this isolated Majorana mode, and you find that it initially decays, but it never decays to 0. It settles down in a plateau. And then you find that this plateau height goes down as you make the system size larger and larger. So what is happening is that this decay mechanism is very different from that of with open boundary conditions. With open boundary conditions, you had one edge mode and the other. They hybridize, so that caused the thing to decay to 0 and oscillate. But here, there is no cousin with which it can easily hybridize with. The only way it can decay is through its coupling to the reservoir. But then the reservoir is not an ideal reservoir when you have a finite size system. That's why initially it goes down, but it gets trapped. Yes, it gets trapped. So this trapping is entirely because of a finite size effect. And that's reflected in the fact that if you make L larger and larger, it actually goes down to 0 more rapidly. And then we can also understand that this is a finite size effect by noting that the height of the plateau is directly related to something known as the inverse participation ratio, but maybe I don't want to go into those details. Okay, so then what about if we now broke integrability in the right way, which is that this is the perfectly symmetric one, where the integrability breaking terms are now also Kramers-Vonnier symmetric. And then we study the decay of the autocorrelation function. Then what you find is that indeed it does still decay to a plateau, but the height of the plateau is higher than what you would have got if you had just integrability breaking terms which were not symmetric. So the difference at this stage is at the level of quantitative. It's not qualitatively too different. So this plateau heights are a little bit higher. So that is what one finds here. So anyway, so as I promised, this is okay. So this was just some work we did where we simulated this 0 mode in the quantum computer. But I think I'm kind of towards the end, so I'll just explain give the conclusions. So basically, by using this language of fusion data, we constructed a bunch of models which have these topological defects. What's nice about this construction is that you can do it for lattice systems, you can do it for Hamiltonian and Floquet systems. And we studied in detail the Ising model, which has what is known as a Kramers-Vonnier duality, and we looked at the duality in the form of a duality twist. What happens is that the twist introduces a Majorana mode, which is present at infinite temperature, but the decay is much slower than if you had, once you break integrability, there's a quantitative change in the behavior of how rapidly this Majorana mode decays if the integrability breaking term preserves Kramers-Vonnier versus if it breaks Kramers-Vonnier. Preserving Kramers-Vonnier in general tends to prevent the system from decaying quite as fast. This way of also getting non-integrable models is related to what is known as weak integrability breaking. And so consistent with that, although I don't have the plot here, if I look at one of the conserved charges, you can also show that it decays slower than what you would get from Evoluru. And so what are the open questions? So right now we have we would like to understand develop a more quantitative theory for time scale, decay time scales when you have these kind of Kramers-Vonnier symmetries to take into account. In addition, we also want to understand the role of multiple defects. So right now we're looking at intersecting defects when you have both the horizontal Kramers-Vonnier as well as the Kramers-Vonnier twist, and we would like to understand what that means for the dynamics. But in general, it appears that this formalism can help give us access to new kinds of symmetries, and that can give us some new dynamics which was absent previously.
Any other questions, comments?
I I can make a small comment. I recognize some formulas from deformation of integrable models that were devised in ADS-CFT integrability, because people were trying to understand what are the most general deformations of the spin chains which stay integrable. So that method that was used by Motrunich and collaborators. So that was developed, I think, by Weisert and Neubert and Barguer. So the idea is that you are adding interactions which are longer and longer range, and they are controlled by this parameter lambda. So I see that there is a smart use of this method to break, weakly break integrability, and that's...
And I would add that what the defect allows you to do is give you a handle on some quantity you can study directly and see how.
Yeah. So that was used in particular for Ising type model?
Yeah, so far we've only done Ising, but there are lots of other models one can study. But even with Ising, there are all these other questions. Like I'd love to know what the intersecting defects do, for example, because you have to resolve the junction, right?
Yeah.
So you have to know this braiding and stuff like that. So it's kind of interesting to see what happens there.
Okay. Thank you very much for the nice talk.
Oh, thank you. Yes.
What happens if you introduce an extensive number of the defects? Presumably you get more Majoranas, but when you then perturb the system, is it less stable?
Yeah, if you perturb the system, we've not done it, but I would expect they're less stable. So if I have odd number of Majoranas, the same story will happen, that you will ultimately have one leftover Majorana, and it will then settle down on this plateau because of finite system size effects. But if you have even number, then they will just fuse together and they'll be gone, because they'll just pair with each other. And
do you have any analytic handle about why it is that the autocorrelation settles down to a value that goes like just one of a polynomial in system size?
You mean the system size dependence? Yeah, unfortunately for the system size dependence, we don't have. It turns out that we do have for the case where you have a pair of them, and then you are having the primary decay is due to coupling to the reservoir, and then you can do like some control diagrams. So you can actually tell where in the parameter space you have lambda square, where in the parameter space you have lambda 4 and lambda 6. So it turns out that if you play with the couplings even in the free fermion limit like J and G, you can suppress Fermi golden rule. Like it doesn't always have to be lambda square, because if you make the bands flatter and flatter, you need higher powers of the interactions to cause decay. So we have handle on that. But for the finite size thing, it's always difficult, we don't know. And this is also related to questions about MBL, and also I know there are people who are really interested, but we have not made much progress. Yes.
With this almost zero modes that you get in the integrability broken case, I mean, do you see that as really basically criterion for integrability, that in this case you can have this real strong zero modes, and whenever you break it, they're gone, or is it just a...
I only know of integrable models that have these strong modes. So even in the Floquet version, I've seen only one interacting integrable model, which is the XYZ chain, which was worked out by Paul Fenley, where you have the zero mode, and then with Lorenzo and Eric, we worked out the Floquet version of this, but it had to be an integral model to get a true long-lived mode. I don't know of any interacting models, and if there are, then they may be rather special still, yeah. Or maybe, I don't know, maybe Sanjay has an answer to that, because he's been doing this commutator stuff.
I mean, but they're kind of fine-tuned, like you need to use the terms carefully.
Yeah, here you summarize that, so you create a domain mode, then isolated mode is created at the domain mode. But during the talk, at some point you mentioned applying some operator to move the domain mode, and but isolated mode remains at the original position or something like that.
Yeah, so the thing is
I
that,
didn't quite follow.
yeah. So, experts in the field, like if you were to ask people like Paul Fenley, they would have said that, if you have this isolated zero mode is formally separating one region where J is greater than G and another region where J is less than G. But we were not thinking of it this way. What we did is when we looked at this unitary, we saw that this was a unitary which contained only odd number of fermions. So you have to have a zero mode no matter what. So it turns out that here there is no domain wall in my couplings, right? Everything, all the J is the same and the G is the same. So, but what is the meaning of the zero mode then? Well, the zero mode is like the limit of zero domain wall width. And to see it, you do this unitary transformation and literally move the twist, and you find that the zero mode is not moving, and the region between the twist and the zero mode is where you have this Kramers-Bonnier transformation. So that's how we understood our results vis-a-vis the older results.
So can it be seen as a general phenomenon that you have an odd number of fermions to have zero modes? Is this something more general, or is it just particular?
I don't know. You're talking about like parafermionic systems or something, where if you have odd number of parafermions, maybe. Yeah, that's an interesting question, because you can take the Potts model and do a twist, and then maybe you can get a model which has an odd number of parafermions. So you could probably see it that way. Yeah.
Just a general understanding.
Yeah, it could be.
If you see this model as coming from spin models, then you have on a odd number of sides, you have the spin has to be a half integer, so you will always have some mode that is
Yeah, I mean there are a lot of other things we could do, but I have not ventured far.
Actually, sorry, just the statement about odd number of fermions. This is a statement you're making about the Hilbert space? I was slightly confused about whether you were talking about a term in the Hamiltonian having an odd fermion parity, or whether you were saying that the Hilbert space.
So the way you should think about this is that there is a Z2 even and there is a Z2 odd sector.
Sure.
The total Z2 even has odd fermions, and the Z2 odd also has odd fermions, and so in total everything is fine. But if I want to solve this model, then I have to be replace omega by a number. If I don't replace omega by a number, there's no way I can solve this, because this is not a free fermion problem anymore, right? So the tool to solve this problem is that you take this Z2 operator and you fix it to 1. If you do that, then you have a strange situation where you have odd number of Majoranas. So you have, if I have a site L, you have gamma 2L Majoranas, but only 2L minus 1 appear in this model. And so then just by counting, you know there has to be a zero mode. But then there's nothing to be upset about, because if I change the sign of omega.
Sorry, just to say, if only 2L minus 1 appear, then there is a Majorana mode that does not appear.
Yes.
And it commutes with this time evolution.
No, it actually doesn't commute, because if it commuted, then I would have had the standard situation where there would have been a zero mode from here, and then there would have been the left out Majorana, which gives you additional zero mode, and then I would have had a pair of zero modes. And then it would be the standard zero mode pairs, and everything would be like the standard situation with a physical fermionic system. The problem is that this is not a very physical system in the language of fermions for the following reason. So you have in this model gamma, like all the Majoranas entering except 1. Now that particular Majorana does not commute with this unitary. But all these other Majoranas that are sitting here inside this unitary commute with omega. So if I want the dynamics of these 2L minus 1 Majoranas, I can just set omega to 1.
Okay.
And therefore, then you find that there is this zero mode that's sitting there. But the left out Majorana actually, if it commuted, then it would have been the other zero mode. But the problem with the left out Majorana is that it actually doesn't commute with the unitary.
Okay, so in an eigenspace of omega, there are effectively 2L minus 1 Majorana.
Yes.
And in any problem, like basically almost, regardless of the details of the problem, if there are only 2L minus 1 effective Majoranas, then there's necessarily zero.
Exactly. But then the other zero mode is now, if I switch the sign of omega so that I'm in the Z2 sector, then there'll be the other one.
Fine.
Any other questions? If not, thanks again.